here, and today's workshop will be going over some common data structures that are in use for pretty much all interview questions. So to start off, just to give you a little idea of where we are in the workshop cycle, we're going to be starting with this week and the next week going over some data structures that you'll need to know for pretty much all algorithms that are going to be covered in the interview workshops, as well as running through some recursion and dynamic programming in the workshop after that, and then some graphs and trees after that. So we're going to really build up the fundamentals for these next 2 weeks before getting to advanced algorithms in the next coming workshops. So to start off, this workshop is going to be pretty code heavy, and I'd encourage all of you to be writing code on your own computers. And as we go through these data structures, we'll use twosome as a sort of example to show how working with different data structures is like in a relatively simple problem. So if you would be interested in sharing the code and getting some of the code reviewed during the workshop, please use codeshare.io to send a link for the code to me so I can screen share it and go over it during the workshop. So to start off, arrays. So anyone familiar with arrays, how are arrays content stored in memory? And you can feel free to just go ahead and unmute or drop the answer in chat. Either works.
They're like stored as like a fixed like set in the same place. So unlike like linked lists and others, it's a fixed like block of memory that's all next to each other, and you can access any element with one step.
Exactly, that's perfect. So to repeat what she said, an array is going to be stored contiguously, which means all of the elements are right next to each other. And the fixed data type gives us the amount of step we need to find a element in the array. So moving on, we're going to be quickly developing all of the methods for all operations to do with arrays before we get to solving a problem with an array. So first of all, Angela's already mentioned how to access elements in an array. So what would you do in the code to access an element in an array? Yeah, perfect. You'd use the braces operator. And as Angela already explained, we already know where the point in memory is in the array. So when we give it an index, we instantly know what memory offset to apply to the array. And that way we know how to get the element directly. So now for the next operation, how would you search for an element in this array, or search for an element with a specific value? So as an example, sorry, go ahead.
You iterate through with like a for loop.
Yeah,
and then you
would iterate through it. And that would be called the linear search algorithm, because if you have an array with a certain amount of space in it, you need to go through the entire array to find the element with the correct value. Now, would this be any different if the array was sorted? Right now, since we're going through every single element, we have an O of n time complexity. But if the array was sorted, is there any difference to this?
I don't know. I don't think so, because if it's sorted, you still have to check to get to the position. Okay, well, yeah, if you like know which position to look for it, like for example, if you're sorting something in alphabetical order, then like perhaps, I don't know. I don't think it's going to be faster.
Yeah, that's a good idea, but there is actually some advanced searching algorithms that allows you to get faster than just checking through the elements. So Jeffrey typed in chat binary search, which is a log n. Jeffrey, do you want to give a quick overview of what exactly binary search is?
You basically start in the middle, and then if it's, and you check if your value is bigger or equal to that, and then each time you can eliminate half the sample space.
Exactly, and that's a great way to explain it. You're going to start in the middle, and since we have an ordering, so suppose we have 1, 2, 3, 4, 5. If we're looking for the number 2, we start in the middle and see a 3. We automatically know that everything below the 3 is going to be strictly less than 3. And since we know 2 is in that search, we've effectively eliminated half of the array. And you keep doing this. You keep jumping to the small subarray and jumping to the small subarray, and this results in a log n time. So yeah, that's a great answer. Now, how would you insert something into an array? So suppose I gave an element and a position. How would you go about inserting that element?
Do you want the array to be sorted or not?
No, in this is just any array.
Well, you have to shift everything by 1 wherever you insert it. And
Yes.
yeah. Also, like if you insert it, you also have to make sure like there's enough space that's in the end or in the back.
Yeah.
Otherwise, you can't ever go out of range. So.
And that's a good idea. Keep that idea in mind. We'll be discussing that a little bit further on in the workshop. So yeah, what Angela said is correct. You want to copy all of the values from the insertion point 1 slot forward so that you now have a space to insert the value. And the time complexity for this is going to be O of n, but is there any way we can get that faster? Like, so what would be the best case scenario for an insertion? Where would we want to insert that element?
If you don't have to keep the order, right, you could just copy or just like move the last element into like, or like basically move the current element like into the last element of the array, which would save you a lot of time.
Yeah, that's perfect. So the best place to insert a value for the lowest amount of operations we have to do would be at the end. And now suddenly we just have an empty space at the end and just place the array element directly in there. So that would reduce the complexity from O of n to O of 1 if we know we always have space and we're always inserting into the end. And I'll keep that in mind for later on. So now that we know how to insert, how would we delete any elements in this array? So suppose I gave a position of the element I want to delete, how would we go about deleting that element?
Can you just like locate the element and then take the last element of the array and just like replace it, and then like reduce the size of your array by 1, or if you have a counter variable somewhere.
Yeah, so that's a good idea. But what that would do is that would change up the relative ordering of the elements. You know how to do it without changing that?
You have to preserve it.
Yeah,
then
preserve
you'd have to
the
shift
order.
everything over.
Yeah, perfect. So what you'd have to do is copy all values further than deletion point 1 slot back. And this will overwrite the value, effectively deleting it and reducing the amount of elements in the array. So now this is going to be an O of n operation also, because every single element past that point that we're deleting, we have to copy it back 1 space. Right, so that's a quick overview of all the array operations. And now let's get into actually using arrays. So what I want you to do here is solve the two-sum problem, but use an array as the only data structure. So if anyone here is familiar with the two-sum and knows the optimal solution, I'd like to ask that you keep that to yourselves until the very end, where we've gone through all of the data structures necessary to provide the optimal solution. So for this, I'd like you to code this on your own laptop, and if you're willing, share it with CodeShare so that we can go over. So yeah, the problem is, let's see if I can get this up on the screen. So here's the problem description. There you go. It's in chat.
Is an O of n squared solution sufficient?
Yeah, that's perfectly fine for now. Okay, to start off the discussion, does anyone have an idea of what type of algorithm they would use to solve this using only an array?
I have a bad one.
Sure, that works.
So if you go through and look for like every value that is less than your target, and then you do a nested loop to look for the complementary of that, then that's a highly inefficient way to get your answer. Like, yeah, I've seen the like optimal solution. I just like don't understand it well enough to replicate it right now.
Yeah, and that's perfectly fine because we'll get towards all of the sort of building blocks that we need to get to the optimal solution. But for right now, what you suggested is fine. So to simplify a little bit of what you said, one way to do it is we have a certain array given some elements. And all we have to do is check every pair of the elements. So this is an example pair. And if the sum of those two elements is equal to the target, we have our answer and we can return that immediately. Right. And that's a perfectly fine way to do it right now. And as Jeffrey said, that would be an O event start solution. So incidentally, does anyone have any code written that they would like to share with the rest of the workshop?
I wrote some pseudocode on CodeShare, so can I share that?
Yeah, for right now, we can share pseudocode, but preferably for all of the problems and when you're doing the actual interview, you want to have working code written. Yeah, and if you would like, you can also code it while we're showing it. But yeah, if you have a code share link, can you send that into chat? Okay, and let me get that up in the screen. Okay, can everyone see the code screen? All right, Jason, do you want to take us through what this code does?
Okay, this is basically just Angela's solution, but in code. So there's two nested for loops, and then so the inner nested for loop is going to start at I plus, or is going to start at one after the first, or the one after the outer for loop, because you don't want to research the beginning. A little bit of optimization for an n-squared problem, I guess. And then we basically just check if the two numbers add up to sum, and if that is true, then just return those two indexes. I'm not sure like what to actually return, but that is the answer, I guess.
Yeah, so that algorithm, that's correct. That does do exactly what the two-sum problem wants. So what you'd want to do is you would want to return an array. Yeah, I see someone's written nice tuple. But yeah, what you would actually want to do here is how would you return an array from a C++ function?
Oh, I would just return array plus I, which is going to be a pointer to the ith element of the array.
Well, yeah, but what this question is asking is you want to return the indices of the two numbers, right? So we have I and j, you have the tuple here. You don't want to return the position, the number in the array that's in that ith position. You want to return the actual numbers I and j.
I think in lead code, they want you to return a vector.
Oh
so
yeah,
you could just
that's
do that.
for right now, we're not using the lead code function headers because we haven't covered vectors yet. But as we go on, cover each data structure, we're going to be re-implementing this or just editing the solution to use those other data structures.
I guess you just pass in an array by like reference and just like return that. I don't know.
Yeah, that's possible. So one consideration you have to do there is, oh, could this return the same element twice? No, it can't return the same element twice. You want two distinct numbers. Yeah, so that's the way to do it. And one consideration you want to make while allocating the array to return is you want to make sure that you don't just directly return an array from the function. And does anyone know why you can't do something like create an array over here? Whoops.
Size isn't fixed at compile time.
Well, we know it's fixed, right? Because we only always return two elements.
The array is going to get destroyed upon exiting the function.
Perfect. That's exactly what I was looking for. So how C++ works with these arrays is if you just declare an array like this, where you declare it locally on the stack, you're going to have the array stack space get reclaimed on function exit. So instead of doing this, you have to allocate it on the heap using the new keyword. And that's just something to keep in mind if you ever want to do stuff with setting back and forth memory. You don't want to send back and forth local variables because they do get reclaimed. You want to allocate it in the heap space. And if anyone wants a little bit deeper explanation of why that happens, you can ask me during the break or ask me afterwards. So let's get back to the slides. That's a great solution. And move on to the next data structure. Okay. So we've seen here, and as someone mentioned earlier, when you're using an array, the size of the collection is fixed, right? And if we want to work with an array-like data structure where the size can change, we want to use a vector. And here, if anyone's coding in Java, if anyone's coding in Python, the equivalents are array list and a list. So a quick question is, what's the difference between a variable length array and a dynamically sized array?
What do you wait? So dynamically sized, like dynamic allocation, or
No, the size is dynamic, so the size can change.
oh, okay. I don't know. I haven't worked with it, so
Okay, yeah. So this might be a little bit of a tricky question since variable length arrays are not really covered. But as of the new C++ standard, you are actually you're actually allowed to give a length for array allocation that's not defined at runtime. Or sorry, not defined at compile time. So yeah, Jacob, it's the other way around. A variable length array is you can declare the size at runtime, and then the dynamically sized array is that you can change the size at runtime. Yeah, it's a good try though. So moving on to the vector operations, can I get a show of hands? How many of you are familiar with the vector data structure? Okay, looks like not too many of you. So we'll take this a little bit slowly. All of these are going to be methods of operations on vectors that are defined by the standard template library. And this is something you will cover in CS32 later. And if you've already taken that class, that should be something you've seen already. And all of these methods are simply provided already. So when you access in the vector, you can access it just like an array with the braces, or you can do it with the vector.add. Now, there's a very subtle difference between these two, and that I'm not going to go into right now, but it is useful to know when you're using this in production or something. So if you'd like, you can check that out after the workshop. What's the difference between the braces operator and the vector.add? So this, again, the time complexity is going to be 0, 1, or O of 1. And that's because we still know that all of the chunks of memory are contiguous. So since we know that all of the elements are directly next to each other, we can again just calculate the memory offset and get the element from that memory offset. So now a search, since it's just like an array, you can actually just do the same thing, a linear search, right? And there is an STL algorithm to do this without having to code the for loop yourself. And you can check that out on your own time again, because this goes into a little bit of an advanced concept, which is iterators, that's going to be covered later in CS32. So this is going to have the same time complexity. It's going to have an O of n since you have to search all of the elements. So as we went over insertion in the array, we had to manually copy all of the elements over and then insert the array element in that point that we just vacated. But the STL provides an algorithm to do this for us already. And that's simply just the vector.insert. And this is going to be an O of n time complexity. So now, as we were talking about before, there is actually a case in which we don't have to copy all of the elements and we can simply just insert the element, and that's an append. This means that you can directly add the element to the end of the vector where there's free space, and as such, is going to be constant time. And now for deletion, instead of having to do the loop where we copy everything backwards again, we can simply use the STL function vector.erase. So now, if you're curious, does anyone know why we can't simply say that the append operation has O of 1 time complexity?
Because sometimes you might need to reserve new memory. For the
That's
new
perfect. Yeah. And here we go into a little discussion about average time complexity and worst case time complexity. So is anyone interested in that? Or I can do that after the break if there's not much interest here and you want to get through the data structures.
Oh, I have a question about the O1. Like, so like, what if every time you append, you're gonna allocate one chunk, like 1 byte of memory, and then add that there? Wouldn't that still be O1? Like, you're just doing 2 things, but it's still O1, right?
Sorry, was your question that when we have an append call, what if we just take 1 byte of memory, add it to the end of the array, and then simply put that there?
Yeah, I'm just like let's say, because I know how it usually works is like after a certain point you like double the size of the memory or something,
Yeah.
or the size of the array. But like, what if instead of doubling it, like what if every time you append you just add 1 more byte of memory at the end and then you insert it? Wouldn't that still be O1?
Yeah, so that's a good idea in theory, but as Jeffrey says in chat, you can't because you need to reserve another location and copy stuff over. And the reason for this is you can't always guarantee that the next byte after the array is free memory. So this goes a little bit into the memory allocation system of the computer. But one of the guarantees that we give as an array is that all of the elements are stored right next to each other in a contiguous array, right? Now, the operating system is the one that dictates which memory is given to allocation calls. And as such, you don't have the guarantee that that 1 byte right after the array is going to be free memory that's available for you to use. It could be in use by another program. It could be in use by like another variable in the program that you've written. So we can't just take 1 byte and add it to the end. So that's why when we make that reallocation call, we actually have to allocate a bigger array and then copy the elements over. That way we have more space for later append calls to have O of 1 time complexity as we keep inserting them. Does that make sense? Or would you like a little like more visual explanation?
Yeah, that makes sense to me.
Okay,
that's
perfect.
fine.
So is anyone else confused about that? It's an important distinction here.
For this, like you wanted, okay, or later on we're supposed to apply it to like the to sum problem. Like what changes really, because we're not inserting really anything. We're just doing the linear search and then using access. Like, I mean, maybe you want to insert for the array you're going to return, but how does this change anything?
So that's right. This actually doesn't change a lot because vectors and arrays are very similar to each other in that they both have contiguously allocated of the same data type, right? So instead of having to change a lot of things in your code, you need to change a very minor amount of code. And some of the changes you can make is here, a big difference between a vector and an array is that the size of a vector is known. You can actually call the method .size on a vector, and that returns how many elements are stored in the vector. You can't do this with an array. You would have to pass in another value that tells you how many elements are in an array to a function that wants to use it. So that's one minor change.
Okay.
Yeah. So again, if you'd like to change your code to make it use only a vector for this two-sum problem. And it should be a very minor change here. Okay, would anyone like to share the code that they've written here?
Wait, how do you do that with CodeShare?
Okay, so if you go into CodeShare and click the share button on the top right-hand corner, you can send the code over on chat.
In 5 minutes, I have to go because I have to watch. the
Wait,
movie.
just like codeshare.io?
Yeah, codeshare.io. There's a button that says share code now, and you can copy paste your code into there and then
Oh,
get
that's
a link
cool.
for sharing.
I think, yeah, because I originally, the solution or like the leak code version uses a
I mean, you can come in my
vector
room.
already. So I think this is just like my original code. I don't know if it's right still because this was a while ago.
That's fine. We can take a look at that anyway.
Can I just copy the link?
Yeah, copy the link and you can put it in chat.
Okay.
And I think we might be setting up a Google Doc with a spreadsheet, so then we can just simply click on everyone's links.
I
But
see.
let me get that up on the screen, and then we can take a look at the code.
Okay. No,
I sent a link.
All right, can everyone see Angela's code? Okay, yeah. So this really shows pretty much all of the changes you needed to make here, which is using numbers.size instead of the a passed in size for the arrays. And this would be the same solution where you simply go through every single pair and then check if it's equal to the target and then return. So yeah, this code looks fine. Some minor things to change would be this else continue isn't needed here since automatically in the for loop,
Yeah.
it'll just keep going. But other than
Mhm.
that, this code is perfectly functional. And don't worry about not having optimal code. We'll get to all of the data structures required to write this optimal code eventually. Okay, going back to the slides, and we'll move on to the next data structure. All right, so does anyone know what the main advantage of array-like data structures is?
Random access.
Perfect, yeah, fast random access. And then what's one of the main downsides of array-like this data structures?
But what do you mean by random access?
Oh, yeah, we can go over that again. So random access basically means an access at an arbitrary point in the array. So
Oh, okay, okay.
suppose
That makes
we had
sense,
an
yeah.
array here. Okay, that makes sense then?
Instant
Okay,
access
we'll
to
keep going.
anywhere. Yeah.
Exactly. Yeah, so what would the disadvantage be?
Fixed length.
Yeah, fixed length
And-
is one, but that's sort of solved in the vector with the dynamic size one.
Like insertion and deletion are slow.
Exactly. Insertion and deletion are slow. And we saw that all of our algorithms require us to copy elements over in order to either remove an element or to put an element in an arbitrary position. So to make up for those downsides, we have another data structure called a linked list. So we're going to see that this linked list has the opposite trade-off, a slow random access for fast insertion and deletion. And now can I get a show of hands who is familiar with a linked list and how it's constructed? Okay, that looks like quite a lot of you. So then does anyone know a C++ struct that we can use to represent a linked list? Or can anyone write one and put in chat? Yeah, and that's about it. So it's going to be a node that contains some data inside it, and then a pointer to the next node. And that's shown over here. So this is an example of a singly linked list, and it's called this because it only has one link to the next node. So does anyone else know any other variants of the linked list design?
Doubly.
Yeah, doubly linked list. So a doubly linked list, for those who aren't familiar, you'd have both a next pointer in the node and a previous pointer in the node. So all of the nodes have 2 links in between them. And does anyone know what we'd have to change in this struct to make a doubly linked list?
Previous.
Yeah, previous pointer, exactly. So then are there any other variants of this design?
I have a question. Is there any reason not to use a doubly linked list or?
Well, that depends on preference. And one of the downsides is that it does need additional memory to store the other pointer. So if you want to use, if you want to use a singly linked list because of that efficiency, that's one of the reasons. But otherwise, a lot of the times doubly linked lists are used for convenience.
Okay.
Yeah, so some other forms of this linked list design that don't actually require any changes to the struct would be a circular linked list. And that's simply a linked list that has a link between the head and the tail. And this can be done with the doubly linked list as well, if you also have previous pointers. And one more thing that should have been discussed in CF32 is the concept of having a dummy node, which is to say that the head node doesn't contain any useful values inside it. And then all of the values, this is where the values actually start onwards. So all of these are important concepts. And if there's any that are unclear, please ask the question right now so that when we get to more advanced questions, you'll be able to use the linked list.
I have a question about the dummy thing. Like,
yeah.
So what's the advantage of just not having anything in H?
So one of the advantages is that it reduces the edge cases for doing operations with the linked list. Because normally when you're considering a linked list, you have to consider a couple of cases when doing any operation. You have to consider what happens if the operation is being performed on the head, what happens if it's being performed on anything in the middle of the list, and what's on the tail, right? And a dummy node at the start of the linked list simplifies a lot of those operations.
Can you like generalize that for everything? So like for an array, couldn't you also make a dummy at the beginning and the end just to like prevent edge case problems?
Yeah, you could, but in the array case here, there's not really much changes you have to make. So for example, take an insertion or a deletion. There's not really much changes you have to make when you're inserting at the first position versus at the end position, because the general case of just moving all of the elements over and then placing the element in the open space, that really just holds for all of the cases. Versus in the linked list, you have to think about pointers to null on the ends, if it's possible, and how to connect different pointers in the linked list, as we'll see when we discuss exactly what to do with linked lists. Okay, so we'll move on to the operations of a linked list. So how would you access an element at a certain position? Oh, sorry, Jacob, did you have a question? I just saw the hand raised.
No, I just forgot to lower it.
Okay, no problem. And Angela, your question was addressed, right? Okay, perfect. So does anyone know how to access an element at a certain position given a linked list?
You have to do like basically iterations, but it's like called something else.
Yeah, so over here, it would be the linear search that we were talking about before, where you have to directly go follow all of the pointers on the nodes and find the specific position that we want, right? Before in an array, since we had the guarantee that we could easily just calculate the memory address from the starting position and the length of the object in memory, we could easily just get the element at the position. And now when we have a linked list, we don't know where they are going to be in memory. So we actually have to follow the trail of the nodes until we get to that specific position. Now, is there any change in searching for a specific element value? Yeah, not really, because in both cases, we would still need to search and traverse the list in order to find the element value. And now the major changes come in insertion and deletion. So does anyone know how to insert a value into a linked node or a linked list in an arbitrary position?
You break up the previous and the next node, and then you set the pointers accordingly.
Yeah, perfect. So to give a little bit of a picture into what Jason just said is if you want to insert a value in between the nodes, what you have to do is delete the link in between, add your node with a pointer to the next node, take the previous node and point it to your node instead. And now you have a list or you have inserted into the list. So now how would you delete something from this list? Suppose this, this node that we just added, we wanted to take it out. How would we do that?
Essentially, you just have to like mess around with the pointers and like clip them and merge them again. To like insert or delete. So it's kind of the same thing, but backwards.
Do you have a more concrete explanation of how you do it?
Okay, so
In this case of a
you
singly linked list?
make the first pointer point to the third object and remove or actually you have to like delete that object first probably or something, and then do that.
Yeah, and that works exactly. So how you do it is just take the previous node, point to the next node, and if you have like all of these dynamically allocated things, you do need to delete them to avoid a memory leak. Right, so that's the set of operations that you would use on a linked list. So now given the linked list, we have the opposite trade-off as the arrays. So instead of having fast random access for slow insertion deletion, now we have fast constant time insertion deletion for slow random access. And now you saw that there wasn't much of a change in the problem when changing from using a array to a vector, but now there is going to be a bigger change changing for a vector to a linked list. So I'll give you guys a little bit of time to implement the two-sum solution, but this time using a linked list. Yeah, and Ryan's put some starter codes for this problem in the chat. So you feel free to use that.
Also, if you do use the starter code, copy it into a new code share, since the links I pasted are shared for everyone.
How'd you get your thing to highlight like your code?
CodeShare has a settings button on the top right. So click the top right here, and then under syntax, change the drop down to whichever language you're using.
What do you think?
Okay, we can start a discussion of the algorithm now. So does anyone have any ideas of how you would go forward with implementing this with a linked list instead of a vector?
seems to be pretty much the same, like in terms of like how you iterate it, but you just have to like change it so it works with a linked list.
Okay, yeah. So what would be the difference between iterating through an array and iterating through a linked list? Like how would you represent that in code? Yeah, P goes to P dot next. And that's one of the most important changes here is instead of having the for loop where we loop through the index in the array, we're now looping over a pointer that just keeps pointing to the next node. And then since we still have to return the index, you have to keep a track of the index and increment the index along with the pointer as the pointer changes. Yeah, Taylor, you can do that. All right, does anyone have any code they'd like to share?
We just learned linked lists in 32, and I'm not exactly super comfortable like with them yet. So no, not really.
Okay, that's fine. That's perfectly fine. And we can just move on to hash maps then, and then we'll have a more concrete review of linked list operations as we go into some of the practice problems, as they're going to be reviewing certain properties of linked lists. Okay, so I think we can move on from here. It's perfectly fine if you guys weren't able to complete that, because we're going to be getting into a better solution for this problem here. So something that we've seen through all of these data structures that we've been going over is we don't have an efficient way to search by value. We see that if we want to get a specific value out of an array or a linked list, we have to iterate through the entire array, the entire linked list, and match the value. So a data structure we can use to sort of expedite that problem is the hash map. And now, can I get a show of hands again? Who's familiar with what a hash map is? Okay, so it looks like pretty much no one's heard of a hash map. So we'll go over this in a little bit bigger detail. So the Java equivalent to this would be a hash map. In C++, this would actually be an unordered map, and in Python, this would be a dictionary. Yeah, I mean, hearing of the name definitely counts. It's good to have exposure to these data structures. So one thing to note here is that there is a difference between a map and an unordered map. And the very simple explanation to this would be that an unordered map simply doesn't have order. Yeah, throwing a hash map at it, that you'd be surprised at the amount of problems that include hash maps in interviews. So something to see here is that a hash map is simply a key value store. So we have a key, and in this example, it would be a number, and that key would point to some value. So we would access this map by saying map of 2, and that would point to Apple. So something to note here is this is something you will be going over in CS32. And the basic concept of the hash map is that each key over here is given a numerical value if it doesn't have a numerical value and assigned a bucket. And that way, when we have a hash map, we have keys that fit into these buckets with the values being stored here. And this allows for really fast access because when we want to get an element associated with the key, all we have to do is know the mapping between the key and the position that it's stored in. And that's what a hash map provides. Now, the difference between a map and an unordered map is that the concept of order in the map means that certain operations are slower. So right now, we're only going to be considering an unordered map and possibly go over exactly what happens in a map in our trees and graphs workshop. So to start off with Hashmap Operations, I know not a lot of you are familiar with this. So instead of going through and trying to see who knows what, we'll just go over the operations, and then you can ask some questions if you're confused about exactly how to use a map. So if you want to access an element in a map with a key, there's a couple of ways to do it. So this find function returns an iterator. And this is another concept that you'll go over later in CS32 if you're in that class. But what we can do is we can combine these two operations. If the find function in a hash map returns any iterator that's not the end of the map, we know that the key exists in the map, and we can simply access it by doing it like we would in an array where we do map of key. And now this is going to have a constant time complexity. As we saw, all we need to know is the key and where it maps to in memory, and that'll give us the value instantly, right? To insert a value into the map. Yeah, go ahead.
For like the general thing, okay, so wait, what's the difference? So you know how you define the hash map as just like a data structure with keys and values, but it seems like there's like other structures like that, like dictionaries and just normal maps, like you briefly mentioned. Is there anything else that defines it as just like a hash map specifically?
Sorry, can you rephrase the last part of that? What do you mean?
Yeah, so like what makes it a hash map and not a dictionary? Because dictionaries are also like key value pairs, right?
Yeah, so the thing that makes an unordered map a hash map is it uses this mathematical function called a hash function to generate the bucket position that gives you where the value is. So this is something that's a little bit complicated and a little bit outside the scope of the workshop. But essentially what you need to know about a hash function is that it tries to assign a key a fixed value numeric value to it, or sorry, fixed size numeric value, right? So what this would give us is we would pass in the key into a hash function, which gives us a numeric value that we can use to almost uniquely identify it to a certain point. And then you'll go over exactly how a hash table is implemented. But what you can think about is thinking about it this way. The thing that makes it a hash map is that we can instantly access the element from the key, right?
Okay.
Other maps, like a tree map or something like a search tree, we would have to go through a slightly more complex operation to actually search for the value in the tree structure, which has a little slower time, like a log-in access time.
I see.
Yeah. Hopefully that answers your question. And if not, you can we can talk about this after the workshop.
Okay.
Right. So to insert a value into the map, this is also simple. You can simply say the map at position key is a value. And this is still in that sort of sense that we have a key value mapping. All we have to do is give it the key and set that to a value. And this is also a constant time operation. And then to delete a value from a map, we simply just erase that key. So this is the most important part of using a map. It's how to access an element in a map, how to insert a value to that map, and how to delete a value from that map. So does anyone have any questions about these basic operations? Okay, so let's move on to, we'll move on to the motivating example, and this time we can actually solve it in the optimal manner. So we know that hash maps provide fast key search, right? So does anyone have any ideas of how to apply that to this two-sum problem?
You
Can you
could
just like generate?
Sorry to interrupt
You-
you.
you
I
can
just
go,
realized
you
I have
can
a
go.
question in the chat. Hash maps seem too good compared to other data structures. Is there a downside to using them? So they're very different from other data structures, right? If you want to keep any sense of order, you can't do that with a hash map. Like when we have an array, we know how the elements are ordered in relation to the other elements. And if that's something you want to leverage, you can't do that with a hash map, right? That's why there's some intermediate results with that tree map that has a sort of ordering and the key search that really has that middle ground between the two. So it's not as comparable to the other data structures. Yeah, and as Justin says, hash maps also have the possibility of hash collisions, but that's slightly above the level of the workshop, and you'll be discussing this in CS32 also. Okay, and looked like either Jeffrey or Angela had an answer to this question.
Oh, like if you're looking for the complement of, you don't have to iterate through or do the nested at the very least, you don't have to do the nested like iteration. You can just search for that exact complement. And if you don't find it, then you can just go on to the next
Perfect.
value.
And that's exactly how you would do the optimal solution. So to reiterate what Angela said, right? When we're searching through an array and we have the collection of numbers, so suppose we have the example, something like 4, 5, 6, 7, 8, 9, right? And we're looking for this target of a sum to 9. Normally, we'd be iterating through, and in each iteration, have a sub iteration to collect every single possible pair. But now what we can do is we use the fact that we have a fixed target, and in this case, we have the target equals 9. We know that if we're at a 4 right now, then we would have to find a 5 somewhere in the array, and this would result in that target sum. So now, instead of having to go through all the combinations, we could simply say, at a position, do we have the complement located before it? And how you would do this with a hash map is, as we're doing this first iteration, so as we do this first pass through, we can take each of these numbers over here and store those numbers in a hash map. So as we're going through an iteration of this, let's change the target to be 17. Right? As we go through this iteration, first of all, we check that there's a 4, right? Since our hash map is empty, we know that nothing that comes before the 4 actually has a complement here. So now all we have to do is in our key value store, we say we have a 4 at position 0. And now when we get to the next point, when we get to this 5 over here, we can simply check the hash map and check that the complement exists in it or not. And as this goes on, we're eventually going to keep building up the hash map with all of the numbers that we see in previous ones until we get to this 9. And this 9, we'll see that the complement gets a value of 0, 1, 2, 3, 4 of 4 in the hash map. And that gives us the 2 indices we need. Okay, and I see a couple of questions in chat. Is building the hash map also O of n? So usually we don't consider building it in the time complexity. something that we would consider when using this hash map is we would consider the algorithmic, all of the operations that we do, their time complexity, and the space complexity that we get from adding a new data structure to our algorithm. So yeah, building things doesn't contribute to this. And generally you can just use a built-in hash map, Jeffrey. I don't think many interviewers would make you build a hash map from scratch unless that is the question. So when you're using these sort of constructs, you can use the standard template library. You can use inbuilt Python dictionaries. You can use hash maps in Java.
For the oven, because is that time complexity?
Sorry, can
It
you
is,
repeat
right?
the first part of that?
The
I was
oven
able
stuff,
to-
the big O
Yeah.
notation has to do with time, right?
Yes. So the big
Right,
O
so-
notation is used in both time and space. So what was the follow-up?
Okay. Because then you said building things doesn't. But then the thing is, like, if you create more variables, very obviously you're going to have like a longer running or like more memory, right? So
Yes.
how does that not affect big O?
Okay.
Is it
Let's see if
because
an
big O
example would
just gives
help.
you a rough, like,
So big O
measure?
essentially gives you the scale of how what your algorithm does scales with input. Oh, I think Jeffrey is asking about building a hash map if the input is given in a different format. You're constructing one as part of the following. Well, yeah, if the problem is constructing a hash map, then you would need the all of the operations that you do in constructing the hash map would be considered in space efficiency and time efficiency. But if you're just using a hash map, instantiating it, like saying like new hash map, that wouldn't count. Yeah. So like for the leak code question, you're given a vector. Yeah.
And then you'd have to convert that to hash map.
You don't want to convert the vector to a hash map. You want to make a new hash map and place values in it. So you would still have the vector to give you the index positions, and you'd simply iterate through that vector, adding stuff to the hash map as you go on. Right. And Angela, what you were saying about the space efficiency increasing with the amount of variables, suppose I had something here where for some amount of times, I'm making a new hash map. Right. Is this what you're asking?
Oh, I just mean like even just like if you went and added a new like unnecessary variable to hold something like a temp, that would affect your time and space, even if a little bit. Like, why does that not affect big O? Like you said, building stuff doesn't matter. It's just like the access and the algorithms they have to run. But then at the same time, isn't variables and or how many you're using also something you should be considering when you're making an efficient program?
Okay, let's see if I can rephrase what I said about the building. I was talking about instantiation of the hash maps, right? But you are right. If you're going to do a for loop, for example, that it creates the temporary variable I that you use to range over everything, right? But now when you run that algorithm for a bigger amount of n, right, that iteration variable doesn't scale with n, right? So that's the first concept is since we're only using that iteration variable once and just adding things to it, that's a constant spacetime.
Oh,
right?
I see. Okay, that makes sense.
Now, yeah, now if you have something where you're building a new vector and then adding n elements to it, right? That's a space of O of n, because as you scale n, that vector is going to grow proportionally to that n, right? Does that make more sense?
Yep.
Okay, perfect. Yeah, sorry, I wasn't entirely sure what you were asking. Okay, so now that we know how to do this problem with the hash map, I'd like to ask everyone to implement this problem. So give the correct solution, and you can go ahead and do this in LeetCode and run it with the test cases. And if you're ready, you can share it on CodeShare. All right, would anyone like to share any implementations they have of this problem? Okay, we'll move into a 5-minute break right now. So if you're not quite done with the problem, don't worry. If you want to finish it up, go right ahead. But if there's any questions about any of these data structures or any of these operations, please ask them now, as we'll be going on to some practice problems where we'll be using these data structures after the break.
How do you implement hash maps in C++ again?
So you would use the STL library implementation of a hash map. So just use an unordered map. And if you want to know the API of that, you can just go to C++ reference. It should have it and what includes you need to do.
Yeah, I don't know. We haven't learned this yet. And then also the syntax and stuff wasn't really fleshed out.
Okay. Do you want me to flesh out some of the syntax? I can do that right now.
I was just
which-
looking at the leak code solution to like try to understand it.
Yeah.
I can do
Um,
that for the code share if you like.
Yeah,
Okay.
go for it. Let me switch to your, is it going to be the same code share link or do you have a different one?
I don't think it's the same one.
Okay, go ahead and put it in chat. All right, I have the link. And let me put it up.
We can always look at it like after the break because it is a 2-hour workshop. Like,
That's true. If you want a break, then we could always do this at the end.
all right.
Like I wrote a solution in Python, but it seems to be a bit buggy, so I don't know if I should share it.
Oh yeah, you can go ahead and share that and we can go over that.
All right, and I'm not sure if like the operation I use is of 1 or something, but I stole Jason's code share.
Okay, let me put that up on the screen. So yeah, since this is done in Python, if you don't know Python, don't worry, it's fine. there are C++ solutions out there, and yeah, so you don't need to pay attention if you're not familiar with Python here. So we'll see def2 sums list in target. Okay. So yeah, that built-in dictionary, that is how you would use a hash map in Python. Right, and the dictionary indexing is done correctly in the first loop also, so that's fine. And for I in hashmap.keys, let me read this one real quick. Yeah, this is fun. So yeah, if you're wondering about the syntax here, you could also just do for I in hashmap, and that would have the same effect.
Wait, really? Oh.
Yeah.
I guess like you only have to do that for values.
Yes, if you want to iterate through values, you would do that. And you can also do it over items if you like. You can do a tuple over items if you want the values.
Okay. This code doesn't work for the case where it's like you're given a list of 3, 2, and 4, and then you want 6.
3, 2, and 4, you want
I
6.
haven't had time to debug it, but yeah.
So let me see what would be wrong with this. So what does it return in that case?
Like 0, 0 for some reason, so it didn't even find it.
Hmm. Let me go over this after the time for the workshop is over. I can go through and debug this. Yeah.
Okay, sounds good. But
Not
the general
immediately
idea is
sequence
correct, right?
Yeah, the general idea is correct.
Okay,
Where another option you could do here is just in the iteration, build the hash map up in an iteration of the list anyway. So something like this,
Yeah.
where you would go for I none and enumerate. So what this does is gives the index and the list. And as you
that's
pass
working.
through it,
Okay.
if the target minus I not in the hash map, you would then simply just, or if it's in hash map over here, then return the number that's in the hash map along with this I. If that makes sense. Yeah.
Yeah, for sure. And so you'd be building the hash map like as it goes?
Yeah, build up the hash map as it goes instead of going through one entire pass, building the hash map, and then another pass through the hash map and going through it.
Yeah. Well, time complexity is still going to be like the same, but
yes, it's going to be the same.
Yeah, it's a little
overall
faster,
time
though.
complexity, but it would be faster. Yeah. Okay, you can go ahead and
I
get
had a question
started.
about sorry.
Oh, sorry. Go ahead. What was the question?
Yeah, I just had a question about like why like searching for the keys is like constant time. Is it because like your hash function guarantees that like you know exactly the positions of each of the keys?
Yeah, pretty much. So a little bit more detail would be that the hash function maps the key to some numerical value, which gives you the position of the bucket that it's in after passing through a modulus function or something. And that would give you where the value is located in memory. Okay, so this section of the workshop, we're going to be going over a couple of practice problems. And how I'll do it is I'll go over the algorithm first off, have a discussion about the algorithm, and then see if anyone can implement it. So to start off, we'll have a warm-up problem, which is to reverse a linked list. So does anyone have any ideas in how you could solve this problem?
Turn the head pointer to the last one, and then just like by iterating down the, I don't remember what it's not iterating, but whatever. You follow down the linked list, find the last node, put the head pointer pointing towards that, make the and then start from there. Wait.
Okay, so that's a good idea. Let's draw it out and then you can keep formulating, right? So that is iteration, what you're talking about, going through each point in a list. So let's have an example of a linked list in these in blue. Okay, so how would you go about this?
Okay. Could you can't redefine a node, right?
No, you don't want to create a
Yeah,
new
you don't want to
node.
mess with that. Yeah. Because the thing is, if I like change any one of the arrows, it kind of backs me in a corner, I think.
That's true.
Yeah.
I could
Okay,
store
I'm not super sure.
a temporary pointer to the next node.
Yeah.
Oh, yeah, that's true. Huh.
Okay, so how would that work?
Sounds.
We have one pointer and a temporary pointer to the next node. What do you want to be doing here?
Then you take the next node's pointer, that content.
Okay.
You or sorry, the first. Yeah, the first one. You find that address. You reverse this first arrow.
You reverse this
And
arrow over
then-
here.
Yeah,
you
and
go like
then you
this.
take. And then you take the first arrow here, the first red arrow.
Yeah.
Oh wait, God. Okay. Yeah, maybe you do need 3 pointers.
All right. Yeah. So that one problem here is when you reverse this pointer over here, that actually gets rid of this pointer. So what you need to do first is actually have a third pointer here, so we know where to move.
Yeah.
Right. And then that would be a perfectly valid solution, what you're mentioning. If we know that we're going to move to this pointer, we can now safely take this link, make it backwards, right? And then move the red pointers over 1. And now we have a set, right? Edge cases are 2 nodes, 1 node, and 0 nodes. All right, how would you deal with those edge cases, Jeffrey?
I don't think I can think of a general solution, so I just hard code them.
Yeah, that's fine. For the cases where you have an empty list or a case where you have one list, it's generally fine to hard code those. So how would you do it in hard code?
If there's like no items, then you don't have to reverse anything. If there's one item, then you also don't have to reverse anything.
Yep.
And if there's 2, you just have to reverse that one like set, and then just move the head pointer.
Yeah. And now something you will notice about the 2 solution is we know that this node always has a pointer, even if it points to null. So we can actually go ahead and use that same algorithm over here. So if we have that 2 pointers pointing over here and here, right? We make the third pointer equal to null, reverse this. And then when we try to move our next pointer to null, that's when we end. So it's still taken care of in that general case. So now all that's left is what do we do with this head pointer over here?
Or you just move it to like the second node.
Well, we have to start somewhere, right? So if we have this head at the very start, we do need to make it so that this head has a new pointer to null. Right? Because the head in the reverse linked list is going to be the tail.
So that's
Does that make sense? All right, go ahead and try to code that. Let's take 5 minutes, see if you can get code on LeetCode going. Also, just for planning purposes, how many of you would be interested in mock interviews after this workshop? Just raise your hand if you're interested.
Like today,
Today, yeah.
are not very ready, but sure.
So we have 2 hands raised and 1 yes from Jeffrey. Okay. Perfect. So yeah. Yeah, we'll be splitting off to mock interviews at around 7:40. So after the next problem. And for those of you who aren't interested, I'll be going over more problems of this sort. Yeah, Michael, you can do head not equal to null, but instead of doing that in Python, it's none. And you can also just do not head to check for none. All right. Does anyone have a solution for this? If not, just raise your hand if you need some more time. All right, perfect. We'll take a couple more minutes. Sorry, Jacob, is that a question or is that just for more time?
Sorry, I keep forgetting to lower.
No problem.
Yeah, I'm kind of stuck on this one, but I have a something somewhat. Is it okay if I
Yeah,
if I
that's totally fine.
Okay.
Yeah, send it over.
All right.
Oh, I also have something. Can I share it or no?
Yeah, go ahead. I'll take a look at those solutions.
Wait.
Okay, so here's Jacob's. And let's see what this is. So a current one pointer at the head, cur one, cur two, and cur three. Okay. So the first case is, that's the 0 case or the 1 case in which you just return head. So yeah, that's good. And moving on to the next case, the cur one dot next is null pointer. Cur two is equal to head dot next. 3 is equal to cur two dot next. So you're initializing these pointers to be at the second node onwards, right?
Yeah. So currently, yeah, sort of. So cur2 is like the second pointer in this list, and then cur3 is the
Yeah.
third pointer.
And then cur one would be at the head on the start.
Yeah.
Okay. So then a while true case, little small syntax thing. You want the true to be inside parentheses. But cur2.next is equal to cur1. So you're going to flip the pointer. Right. And if cur3 is null pointer, so cur3 is going to be the one 2 after this, right?
Yeah, cur3 is 2 after cur1 and 1 after cur2.
Okay. Yeah. And I think that is a sufficient break condition. Okay, so here we are setting cur1 equal to the next one. Then the middle one to be equal to the third one, and then third one to be the next to the third one. Okay, yeah, so this looks fine to me.
Yeah, but I didn't return anything. I should probably return a cur2.
Yeah. So what is it asking you to return here?
The head of the modified
Yes.
linked list.
So then, yeah. So then returning cur2 would be the correct choice because you're breaking when cur3 is null.
Got it. Yeah, so that's probably what I should return.
Okay. And then taking a look at Jeffrey, were you putting yours in chat?
No, but I just thought of a solution, but it's bad. So
Okay. Sorry, who else wanted to have their solution reviewed?
Yeah, mine.
Sorry, Daniel. Yeah, go ahead and put that in chat too.
There's that. Oh, co-share?
Yeah, co-share.
Cool. Can I just replace all of this?
No, make your own co-chair running. So just go to the website, click share, and then go to the next one. And meanwhile, we're going to be opening breakout rooms for mock interviews. So Daniel, after you're done sharing your code, you can go ahead and go into your breakout room.
This will work like this.
Yeah, perfect. Okay, so prior is equal to head. If head.next is null pointer, return. Okay, so this is already going to break in that first case. So the reason you have both of the cases checking if head is null and if head.next is null is because that first check for head is not equal to null ensures that you don't have an empty list.
So,
right? So
right.
if head is null pointer at the very start and you try to give it a pointer reference to next, that's going to stack fault.
Yeah, okay, that's probably what I should have checked properly. I forget that head is not a node, it's actually a pointer.
Yes. So then going on to the current is equal to prior.next, right? That is fine. And if cur.next is null pointer, return. Okay, so if you set the prior to head and then you set current to the one after head, right? And then check if after that there's a null pointer, what's going to happen is you're not actually going to reverse it in that case, because you know that there are two nodes that exist and then it ends. And then, do you see what I mean?
Yeah, I messed up on those edge cases, I guess. I should have thought about it more carefully.
Yeah. And that's always something to keep in mind when you're doing these problems. You want to make sure your edge cases work. So now let's get to the current case. So now you have the 3 pointers. Setting prior dot next to null pointer. That's in the case that the head is. So that's fine. And then while its current is not equal to null pointer, that's fine also. Current dot next is equal to prior.
And then I shift
And then-
everything.
Yeah.
I just shift all the pointers up. It's hard to read it, but if you draw it out, that's kind of what happens.
And I think this is fine. And then head is set to current and then return. That might be a small mistake because when you're ending on the current not equal to null
Yeah.
pointer,
It should be the prior.
it should be the prior. Exactly.
I put that in and then I made a fix to the while loop.